Hello everyone. Today we will do a problem solving and I chose a problem from Russian National Olympiad. It has a medium difficulty. So let's get started. Alright, here is our problem. So let's read it first. It says hydrocarbon 1 is extracted from low boiling fractions of petroleum pyrolysis using rectification. Hydrocarbon 1 slowly dimerized to form a single product 2, which can be converted back to 1 at high temperatures. And the homologue of 1, compound 3, was first prepared by Wilcox in 1960 through a multi-step synthesis starting from 2-methylcyclohexanol, and here is the synthesis, and they ask us to draw the structural formulas of all ciphered compounds. First thing first, here you see a lot of sentences, bunch of words. What we are gonna do first is to write them in diagram form so that when we need to look up for information, it's easy. So what I'm gonna do is I'm gonna convert these sentences into a simple diagram. So this is what we are given. We have petroleum from pyrolysis, we get hydrocarbon 1 and 2. 2 is the dimer of 1, they are interconverting to each other. And homologue of hydrocarbon 1, homologue means there's a one or multiple CH2 difference between two compounds. So homologue of hydrocarbon 1 is compound 3, and this is what we are gonna synthesize. So I'm not saying that all of this information are going to be useful to us. It's just that I converted this text into diagram form. So you have to take a note of these kind of things when you solve the problem so that you can easily refer to whenever you need to. So now going back to the question. So let's focus on the synthesis. And as I can see from this part of the text, there's nothing useful that could help me in order to find out the structure of any of these compounds. This is just talking about hydrocarbon 1, which is not even in this synthesis. And 3 is, it says it's the homologue of 1. It's just here, but there is no specific piece of information that I can use in my synthesis. Also, there is no any information here. It just says draw the structure formulas. There is no any spectral information. There is no any molecular formula. There are some molecular formula, but they are within the synthesis. So we are going to focus on the synthesis itself without any extra information. So the first, what we are going to do is we are going to try to find out what these reagents do, just to have a rough idea of what is going on. So I'm going to label each step, each reagent or set of reagents with their purpose. For example, this system dichromate in the presence of sulfuric acid, that is commonly used for oxidation of alcohols. Here we have methylation reaction. We have a base, it's going to deprotonate an acidic proton and it will install a methyl group. This step uses a very strong oxidizing agent, nitric acid. So I am expecting some oxidation here, and this compound C, I am expecting it to have a lot of oxygens connected to carbon. And then I know for sure that this is used in reduction. So I'm expecting some aldehyde or ketone to be reduced to alcohol here. And this is N-bromosuccinimide. This is mainly used as brominating agent. And lastly, pyridine, which usually functions as base. So these things I put here, these labels that I have attached to these reagents, we are not 100% sure about their labeled purpose, but it is just for us to give a rough idea of what is going on. So I know that maybe I have to expect an alcohol for G. I have to expect some ketone or aldehyde for compound F. I am expecting some strong oxidation reaction here. You have these kind of rough ideas. It's very useful for us to pre-label so that we can start our synthesis with as much as information possible. So let's focus on the first part, because as you can see, there is some information given for us for compound D, and then there's no any other structure given. So that probably means we should be able to find out the structure of D using the combination of previous information, the set of reagents leading to it, plus its molecular formula. So I'm going to focus on this part of the synthesis first. And first step, as I mentioned, this is used in oxidation of alcohol, and I have alcohol, secondary alcohol. So I'm going to oxidize it and it will form a ketone. So this is very easy, right? And now we are going to talk about the deprotonation of this ketone A, because we are using a base here, sodium amide. So let's take our ketone A, and as you see, this is unsymmetrical ketone. So it has two sides. More hindered side here. The base is going to approach and take a proton from here. And the resulting enolate is going to be obviously more stable because it's more substitute, as you can see. So it's a tetrasubstitute compound, if you remember from alkene stability. It's like a tetra substitute, so it's obviously more stable in compared to this enolate, which is only tri substitute. So this is tetra substitute and this is tri substitute. So obviously I expect this enolate to be more stable. And since this is more stable, I am calling it a thermodynamic enolate. And in order to make this, I need to use less hindered base like sodium amide, sodium hydride. On the other hand, for this one, which I call as a kinetic enolate, I need to use kinetic conditions like lower temperature, more hindered base like LDA or tetrodotoxide. They can come from less hindered side, take the proton and make a kinetic enolate quickly. Yes, it's not stable, but it's gonna form very quickly. So since in this specific synthesis step, we are using less hindered base, sodium amide, our product will be thermodynamic enolate. Once we have this, it's gonna attack to our electrophile, which is methyl iodide, and it's just a simple SN2 reaction. So we are gonna install a methyl group here, and our next step would be complete. And now we get our A and B. So as you can see here, this is our compound B. Now let's try to find out the structure of C and D. So let's do some counting here. This compound has 7 carbon atoms, and this compound D, as you can see from molecular formula, has 12 carbon atoms. So what happened here is that you have added 5 carbon atoms. We already added 1 here by installing a methyl group here. So from B to D, we need to add 4 carbons, right? Because total there's a 5 carbon increase. And we know that this is a strong oxidizing agent, so it's not supposed to bring any carbon atom. So that leaves us with this information that from C to D, we have to have 4 carbon atoms. So it's like 2 equivalent of ethanol we are gonna use. So because I see from C to D only 2 carbons, but from B to D, I need to add 4 carbons. So that means I need to have 2 equivalents of ethanol. So that's just, again, what we can get from this limited information about the reagents and also number of carbon atoms. But now let's calculate HDI. So in the next slide, I'm going to show you what HDI is, how to calculate it, and how is it helpful for us in helping out determining the structures. So here is the molecular formula of compound D. We are given this. And here this is like 2n plus 2, where n shows the number of carbon atoms. This helps us to find the maximum number of hydrogens. So in this specific compound that have 12 carbon atoms, maximum we can have 26, not more than that. But we have only 22. So the difference between the maximum number of hydrogens and the number of hydrogens that exist in the compound divided by 2 gives us hydrogen deficiency index, or you can call it as elements of unsaturation as well. And oxygen, sulfur, we don't usually count them in HDI calculation. And halogens, fluorine, chlorine, bromine, and iodine, we treat them as hydrogens when we try to find out HDI. We will have a lot of examples where we will need to calculate HDI because it actually gives some structural information. For example, in this specific case, HDI being equal to 2 implies one of these 4 cases. It can have 2 rings because 1 ring contributes to 1 HDI. It could be 2 double bonds or a combination of a ring and 1 double bond, or it could be a triple bond. So 1 HDI means either a pi bond or a ring. And here are all possibilities basically. So now we are going to combine this HDI information with the information of the reagents of the next steps, and we are going to combine them and in order to find out hopefully something useful about the structures. This reaction here, so we already know that this compound D has HDI2, and this reaction of converting from C to D, this is actually a Fischer esterification. And we already know that this should be 2 equivalent. We find out that from counting the carbons. This should be 2 equivalent. So what does that mean is that compound C should be dicarboxylic acid. So it should have 2 COOH groups somewhere like this, so that I can install 2 of these ethanol in the presence of acid catalyst. So Fischer esterification looks like this, RCOOH, and we take another alcohol in an acidic environment, and then they just combine to give an ester. Since I am using 2 equivalent of this, I need to have dicarboxylic acid so that I can install ethanol on both sides. Now let's combine all of this information together. Now I know that from B to C it's going to be strong oxidation reaction. C should be dicarboxylic acid, and then we are going to have Fischer esterification to yield a compound D, which has HDI of 2. And this HDI of 2 probably means 2 double bonds because we need decarboxylic acid, right? And from C to D, we don't have any change in HDI. And since this should be decarboxylic acid, and this is very strong oxidizing agent, I am thinking about cleaving carbon-carbon bonds. So there are two possibilities. These carbon-carbon bonds between carbon number 1 and carbon number 6, and also carbon number 6 and carbon number 5, these are the most susceptible to cleavage by a strong oxidizing agent like nitric acid. So I have two possibilities. One is I can break the bond between carbon 1 and 6, and I will get this compound. And what I do is I break the bond between carbon-carbon, and I just attach OH to this side. OH, or depending on availability of hydrogens, I can go all the way to COOH. For example, when I break this bond, I have carbon 1, this is carbon 1, this is 8, this is 9, and this is 2, and the rest of the ring. So I have only one hydrogen, let's say, one hydrogen, I'm just writing it in parentheses. So there's only one possibility of oxidation, so I can make it OH. So that's why I get this part here. And when I break it for carbon number 6, I already have one CO. So what I can do is I can add OH group here. So this is how oxidation works. And this compound you see here would be a result of the cleavage of the bond between 1 and 6. And this, the same idea apply. You just put OH groups. If I break the blue bond, then carbon number 5 here, as you can see, it has actually a potential of 3 hydrogens. So I can oxidize it all the way to COO. So intermediate step would be like, and then aldehyde, and then carboxylic acid. So you can think of it as a step-by-step oxidation all the way from alkane to alcohol to aldehyde and then carboxylic acid, because nitric acid is a very strong oxidizing agent. It will not leave it as alcohol. And between these two possibilities, honestly, both of them are possible. But since we need the carboxylic acid, this one I will choose as the structure of compound C. So actually, without needing to look for the rest of the synthesis, we are able to find out the structure of C, which is the decarboxylic acid, and structure of compound D, which is you can call it D ester. Now that we have a structure for compound D, let's solve the next part of the synthesis. And here we have compound D, and then going to E and F. And as you can see, F has the molecular formula. So let's apply similar counting process to develop an idea on what could happen in these two steps. So as you can see, compound D has 12 carbon atoms. You can see from both molecular formula and from the structure that we have found. And compound F molecular formula, it says that it has 7 carbon atoms. So let's calculate HDI again, because we have full molecular formula, in order to gain an insight towards the structure of compound F. So yes, again, using the same formula, we calculate the maximum number of hydrogens and the hydrogen deficiency index of 2, and it could imply again one of these things. Now having HDI calculated, let's see how it can help us. So since we are using a base on D ester here, followed by decarboxylation conditions, we can propose a Claisen condensation here. And HDI of F helps us a lot here, since we know that we should have 2 elements of unsaturation. Indeed, intermolecular Claisen condensation will yield a ring. So we would have a ring, because we are just applying a base to D ester. So this would cyclize, and we would have a ring here from the Claisen condensation, and a ketone double bond. So having one ring and one pi bond would yield of HDI equal to 2, which is in a perfect alignment with our calculation. So let's see the mechanism and the structure of E as we propose a Claisen condensation here. So what's going to happen is a base, sodium ethoxide, is going to deprotonate. So we have actually 2 sites, but there's no any hydrogen here. So it's going to deprotonate here. It will attack nucleophilic acyl substitution, will go up, carbonyl group will reform, and then ethoxide will leave. We will have this compound, and actually compound E is this one. So most people here are confused, and they might show this as the final structure for E. But as you can see, there is no, as you go in the previous slide, there is no any quench step, there's no any workup step, there's no any water, there's no any proton source. So this compound E is actually this one, because Claisen condensation goes all the way to deprotonation. Actually, this step is very important here, because this is what drives the whole Claisen condensation reaction. This should be the compound structure of compound E. And now we got our compound E, which is subject to decarboxylation. And we show mechanism in the next slide for this decarboxylation. So we have compound E, and we have potassium hydroxide in the first step, which is going to hydrolyze. So it's going to be like a base catalyzed hydrolysis of ester. And we are going to form again this compound, because since we are using a basic condition, we cannot have OH here. It's going to be O minus. So we have like the anion here. And then it's going to be protonated in the second step. We will have CO, and this will be protonated, and this will be like carboxylate anion, become carboxylic acid. And then with a bit of temperature here, we are going to lose carbon dioxide, and we will form an enol, which is going to be tautomerized back to ketone. So here I forgot to put two methyl groups, so sorry for that. And now we have the structure of compound E, which is going to be a sodium salt. You can show it like this, a negatively charged anion coupled with a counter ion, which is sodium plus here, because we are using a base with a sodium. And then the structure of F is going to be this, a ketone. It has indeed 7 carbon atoms and 2 HDR, 1 ring and 1 double bond, and just 1 oxygen. And this is going to be really easy. It's a reduction. So if you remember the first slide, we said we are expecting a ketone or aldehyde for F, and we are expecting G to be an alcohol. So indeed, this is what happens, and we get our secondary alcohol. So let us zoom out and see the overall synthesis again. And we found all the way until G. And let us focus on the last part of the synthesis, from G to compound 3. So we have the structure of G as a secondary alcohol. We already know that. And what's going to happen in case this is anhydride and this is alcohol? So what's going to happen is we are going to convert hydroxyl group into a better leaving group, an ester, so that in upcoming reactions it can leave better, because hydroxyl group itself is really bad leaving group. And as you can see here, we have high temperatures, which suggest a possibility of elimination. And this would yield us a compound with a double bond. And obviously what could happen here is that we can use water maybe in the system, and this could deprotonate like this. So we have a base. It could go here, and it can go like this. So we will have a double bond here, and that could be the compound J. And this is N-bromosubcunimide, as I introduced in the first slide. It's a brominating agent, and what's going to happen is a radical bromination at allylic position. Because this is radical bromination, right? So we are going to start with a proton abstraction, and a proton is going to be abstracted from the weakest CH bond. And what is the weakest CH bond here? Obviously this bond. Why? Because when we break this bond homolytically, we are getting a radical at this point, and this is very stable radical. So radical stability is inversely proportional to the bond strength. The more stable the resulting radical is, weaker the H bond is gonna be. So now actually this is quite easy, because now we have a base. Pyridine functions as a base. So it's gonna be a similar reaction from H to J, elimination reaction, and you will get this compound. And as you can see, this is quite symmetric compound. This is not guaranteed to be 100% sure every single time, but when you have this kind of synthesis, you usually end up with a nicely looking structures, like something symmetrical, something extraordinarily beautiful structure. So this is actually quite symmetrical, and that actually also confirms our whole synthesis, that we did all the synthesis to get this nice symmetrical molecule. And now we can put this back to this initial slide that I showed you. So compound 3 is this one. Hello everyone, welcome to part 3. In this part we are gonna try to find the structures of hydrocarbon 1 and 2. Let's get started. So now we have a structure for compound 3, and if we number from here 1, 2, 3, 4, 5, it's gonna be 5, 5 dimethyl cyclopenta 1,3-diene. That's the name, IUPAC name for this compound. So because the question asks us to find the structure of compound 1 to 3 and A to J, and we found all ciphered compounds in the previous slide, but we only found compound 3, which was the last compound of the synthesis, but we didn't find the structure of compound 1 and 2, and that's what we are gonna do right now. So the only information that we have is that hydrocarbon 1 is homologue of compound 3, and it dimerizes to hydrocarbon 2, and that's the only information we know, and we also know their boiling points. And actually this is the only thing you need, because if you go back here, we have the original problem in the previous slide that we showed last time, and then here we have compound 3. We got it through the synthesis, and there's no any other piece of information in order for us to find the structures for 1 and 2. It's only this part, and we have converted this part into a diagram form, so we are going to use the same diagram. Unfortunately, in compared to previous case where we had a full synthesis, we have set of reagents and sometimes molecular formula and some other piece of information that could help us in order to find out the structure of molecules. In this case, we don't have a lot of information. Unfortunately, we only are given this bunch of sentences which we converted into diagram form, as you can see here. But other than that, we don't have any information, so we have to see what we are given. So this is homolog. So what is homolog? Homolog means the series of compounds that differ from each other by 2 groups. You add CH2, you get another homolog. Add another CH2, you get the next homolog, and so on. So we know that we don't have any other functional group. We don't have to introduce any other atom. So this is just one CH2 more or less, or maybe multiple CH2s more or less. For example, methane, ethane, propane, butane, and so on. They are like homologs of each other because every single time you are adding one CH2 group. So now we know that it's homolog, so we can go maybe 1 carbon less, keeping the similar structure, 1 carbon less. Maybe we can remove one methyl group here. That's one possibility. Or we can add another methyl group somewhere here. That's also homolog. But one key piece of information here is that boiling point of compound 3 is higher than boiling point of 40. So hydrocarbon 1 should have less number of carbons in compared to compound 3. So why this is the case? Because these physical properties like boiling point, conductivity, crystal structure, and so on, these properties are directly related to intermolecular interactions, which in turn are dependent on many factors, including molecular size. So there's no a direct relationship between number of carbon atoms and the boiling point. So there is something in between, and that is intermolecular interactions. So stronger the intermolecular interactions are, higher the melting and boiling points will be for specific compound. For example, that's why alcohols have higher boiling point in compared to the molecules that have the same molecular formula but have ether functional group, because ethers do not have hydrogen bonding, but alcohols do have hydrogen bonding. When you have hydrogen bonding, it means there's higher intermolecular forces. It's going to be much harder to break those intermolecular interactions to send molecules from liquid state to gas states, in other words, to evaporate them. So that's how we set up the relationship between physical properties like boiling point with intermolecular interaction and then molecular size. So here, because this compound is not polar, also it doesn't have any electronegative atom and electropositive hydrogen atom, so we don't have any hydrogen bonding, we don't have any dipole-dipole or ion-dipole interaction. So the only interaction here is van der Waals interactions, or you can call it London dispersion forces. And London dispersion forces are dependent on 2 factors. First, molecular weight. Higher the molecular weight, stronger the London dispersion forces, higher the boiling point will be. Second factor is surface area. If 2 molecules have the same molecular weight, then we have to take a look at their surface area. So in this case, because this is homolog, obviously we are going to have different molecular formula and different molecular weight. So we need to find something that has less number of carbon atoms, like lower molecular weight. So in this case, we can think of 2 possibilities. One possibility is just we remove one methyl group and we are left with something like this. Or we can be like this, just 2 methyl groups. We can go lower than that, but then we have to destroy the ring structure. So that's no longer homolog. We are going another function group or something like this. So basically, if we narrow down our search space, we only have 2 possibilities here. There's actually one very strong evidence here. Why we are gonna choose this as our hydrocarbon 1 rather than this? Because this one, methyl cyclopentadiene, exists as a mixture of isomers. So we dimerize hydrocarbon 1. If we think that this is 1 and we dimerize it, we are gonna get actually multiple products. So because this itself exists as a mixture of isomers. And why it exists as a mixture of isomers? It is because 1,5-hydride sigmatropic shift. So this compound, as you can see here, has hydrogen. So what can happen is this can move here, this moves here, and this moves here. So this is one of sigmatropic rearrangement where your electrons are moving around the cycle. So we call this as a pericyclic reaction. So what could happen is we can get another isomer of this compound, which would have methyl group and double bond in a different position. So a double bond will be here, methyl will be here, and this will be here. So if we can name this as 5-methyl cyclopenta 1,3-diene, okay, we just number it 1, 2, 3, 4, 5, then it's 1,3-diene and with methyl in 5th position. But this one is 1, 2, 3, 4. It's the same 1,3-diene but 1 methyl. Okay, this is called 1,5-hydride sigmatropic rearrangement. This is one class of pericyclic reaction. Actually, Diels-Alder reaction itself is also pericyclic reaction. Like you have this diene and you have alkene. This moves here, this goes here, and you end up with pi bond and 2 sigma bonds forming at the expense of 3 pi bonds breaking. This is also one example of pericyclic reactions, and this happens in just room temperature, so you don't need to have elevated temperature or something like that. So if you have 5-methyl cyclopentadiene, it's gonna isomerize to 1-methyl or even 2-methyl. You can have many rearrangements, so you will get isomers. So if you choose this compound as your hydrocarbon 1, it's basically impossible to have because it will have its isomers as well. When you have dimerized them, you will actually have many dimers. Okay, does not make sense within the context of this question. Now we know that we cannot propose this compound as our hydrocarbon 1, so I would go 1 carbon lower and I would propose this cyclopentadiene 1,3-diene as my hydrocarbon 1. And so since we have found the structure of hydrocarbon 1, the next part is easy. We are gonna dimerize it. So what's gonna happen is intermolecular Diels-Alder reaction, but between the molecules of the same compound, same hydrocarbon 1, and we are going to get this compound, and I will show you how we will get this one. So in Diels-Alder reaction, just as I showed you before, you should have this and this. So this is alkene part, and this is diene part. So basically, ene and diene, they come together, they make a cyclohexane ring. Here, this compound will actually act twice, once as a diene, once as ene. I'm gonna write both of them at the same time. So this is in diene form, and I'm gonna write the same thing, slightly rotated form, at it's using its ene part. Okay, then we are gonna have simple reaction. The double bond will move here, this will move here, and it's hard for you to visualize. Just think of it like this. So 1, 2, 3, 4, 5, 6. So we are gonna make a 6-membered ring, and that's this here. 1, 2, 3, 4, 5, 6. If you want, you can even number, right? So let's do this. 1, 2, 3, 4, 5, 6. And this is 1, this is 2, this is 3, 4, 5, and 6. And that makes perfect sense, right? Because I have a new bond between 1 and 6. I have new bond between 1 and 6 and 4 and 5. So 1 and 6 and 4 and 5, these are my new bonds. And I am making a new pi bond between 2 and 3, which is reflected here, 2 and 3. So when you number things, you don't even have to put these are not IUPAC number. You can even put ABC or XYZ, whatever you want, as long as you can track which atoms are in the reactants and then in the products. When you do that, it becomes easier. And as I can see, there is this part that's like that's connected to 1 and 4 at the same time. So you see, I have this carbon atom, I call it as bridge, connected to 1 and 4 at the same time. And then the rest of the compound that comes from alkene part, it's here. So if you just number it in this way, it becomes much easier and you can easily get the structure of dimer. So now we found everything from A to K and compound 3 as a part of synthesis with some bit of judgment. And we found hydrocarbon 1 and we do Diels-Alder reaction, dimerize it to get hydrocarbon 2. And actually 2 can also go back to 1 with retro Diels-Alder reaction. So we call it retro Diels-Alder reaction. Happening here is that we just put the arrows in reverse order. Okay, we will just do this. So this will go here. This is called retro Diels-Alder reaction. So I'm gonna reconstruct 2 cyclopentadiene again. Okay, so if we go back to original question, now we have solved part 1. So it took us a lot of time, but finally we were able to find out all the structures of ciphered compounds as well as hydrocarbons 1 to 3. Now let's continue with the rest. And it says we want to obtain J through dehydration of G in acidic environment, but we get L instead of J. Again, long sentences, a lot of information. it's not helpful. So we need to put in a diagram form. So I go back to the part of the synthesis where we had J and G. So, and this is J. And what happened here is that they wanted to try to get compound J, this one, from G using acidic environment. So I'm just going to show it as hydrogen plus, but it didn't work. Instead, when you take G in acidic environment, you got L. Now we need to draw a structure for L. So we have compound G, which is secondary alcohol, and we need to find out what could happen here. What would be the interaction of alcohol, a secondary alcohol, with a proton? So now we have to think about potential interaction. Also, we have to keep in mind that we are trying to have elimination reaction. Let's take a look at the original reaction from G to J. So what they did here is actually elimination, but as we know, we have two types of elimination, E1 and E2. Here, what happened was E2 elimination. So what they did was actually not from G to J, but from H to J. So when they get H, which is the similar structure, but much better leaving group, what they did was they took a base and there's a beta hydrogen. So it comes here, this goes here, and O acetate leaves. So this is called E2 elimination, and it gave a product. But now when you are using hydrogen plus, we are not going to have E2 elimination. We are going to have E1 elimination. So OH is going to attack to hydrogen plus, and then water will leave. So this is going to be the first step, which we call as unimolecular reaction. It's going to attack here. It's going to become OH2 plus, and then it will leave as water molecule. So we are going to have a positive charge here. And ideally, because we want to get J, what we can do is this, actually, the water that leaves can act as a base and remove a proton from here through this reaction, and we can get our J that we actually desire to obtain, but that doesn't happen because of carbocation rearrangement. So as you can see, when H2O leaves from the original alcohol G, we get a secondary carbocation, but there's a chance for a shift so that we can get a tertiary carbocation. And this is something that's impossible to avoid. So if carbocation rearrangement can occur, they do occur. There is no way to prevent that from happening because it's intermediate, right? It's a carbocation intermediate. It will see that, oh, there is something more stable. So always tertiary third degree carbocation is more stable than the secondary, which is more stable than primary, which is more stable than methyl. So the reason why we are having this trend is because when you have tertiary carbocation, you have a positive charge surrounded by, let's say this is a carbon and it's surrounded by, let's say, 3 alkyl groups. And this is the effect we call as hyperconjugation. So the bonds that are neighboring to this positive charge, they have some electron density and they are donating this electron density through hyperconjugation. So because this carbon plus has empty p orbital, it's an electron deficient. So it wants to get more electrons from electron density to itself so that it can be stabilized better. So that's why when you have tertiary carbocation, you have more neighboring bonds around positive charge, around empty p orbital. So which means you have more chance to stabilize it. So that's why tertiary is always going to be more stable than secondary, which in turn is more stable than primary. So this effect, this trend is explained by hyperconjugation. So it's impossible to avoid this from happening. Intermediate will always try to go to another intermediate, which is more stable. In this case, secondary carbocation will try to move toward a tertiary carbocation, and this is called methyl shift because we are shifting a methyl group from one carbon to another, and by doing so, we are also shifting the position of positive charge from this carbon to this carbon. Our goal here is to get tertiary carbocation, and we get our tertiary carbocation, and then we do elimination here. So there's hydrogen, and again, water acts as a base. This attacks here, and this moves here. So this is E1 elimination after carbocation rearrangement. So this is gonna be the structure of L. Now we are done with question number 1 and question number 2. Let's go. This is the next part, and it's really interesting. So we have hydrocarbon 1, an exothermic reaction with 2 different geometric isomers M and N at 20 degrees. We have 2 compounds in the case of reaction with M and a single compound Q in the second. So we need to write structure formulas for M and Q, and we are given some another fact, that O, P, Q all have molecular formula with 9 carbon atoms, 10 hydrogens, and 4 oxygens. First thing first, again, we have a bunch of words, sentences, we don't like them. So what we need to do first is to convert them into diagram form so that whenever we have any information that we need to look up, we don't have to read the entire sentences again. Just the diagram chart form is always easy. So we just convert it. We have hydrocarbon 1, M reacting with M to give O plus P. With N, it gives Q. And all of them have the molecular formula given. And maybe we can also add 20 degrees. Maybe at this point, it's not important, but we can just write it here as, okay, these reactions have been carried out at 20 degrees. And since we are given molecular formula and this M and N are geometric isomers and this is diene, and previously we have done some Diels-Alder reaction or pericyclic reaction. So we are assuming that it's just, we don't have anything else formed, right? So we have just hydrocarbon 1 combined with M to get O or P, O plus P, or for example, hydrocarbon 1 combined with N to give Q. So we can do this molecular formula subtraction thing. We know the molecular formula of OPQ. Let's just use the second reaction, hydrocarbon 1 plus N to give you Q. Q has the molecular formula C9H10O4, and hydrocarbon 1 has the formula C5H6. It's just a 5 carbon, 6 hydrogen. So we can just subtract it to get this molecular formula of M and N. It's same because M and N are geometric isomers, so they obviously have the same molecular formula. So this thing, does it work every time? No. But in this specific case, because we know that first, when you look at this compound, you know that it doesn't have a lot of functional groups. We are not expecting crazy Grignard reaction, alkene metathesis, Witting olefination, those kind of reactions. We do not expect here. Or aldol condensation, Claisen condensation. We don't expect any of this, right? Because that's not a crazy molecule with a lot of functional groups. It's just the diene. And M and N are geometric isomers. So what is geometric isomers? It's actually cis and trans, right? Usually that's the most common example of geometric isomerism, cis plus trans. So what does it mean? When do we have cis and trans? We only have that in alkene. So M and N are alkene, and this one is diene. So the only possible reaction here is obviously Diels-Alder reaction of this type. We have diene here, alkene here. They react with each other. They give a cycle like this. So as you can see, you can just add up their molecular formula. For example, in this case, it's C4, H1, 2, 3, 4, 5, 6, H6, plus this one is C2, H4. When you add them up, it's just C6, H10. So you literally add them up because there's nothing else, right? And according to the law of conservation of masses, we have to keep the same number of atoms on the both sides. Since we do not have any byproduct, we can literally add the molecular formulas of the reagents to get the molecular formula of the product. So here we have the molecular formula of the product. We have the molecular formula for one of the reagent, which is C5H6. So we can easily subtract. So my point here is that it doesn't work every single time, but in this specific case, when we are sure that our reaction is pure combination reaction with no additional side product. So by applying this chain of salts, we find out that the molecular formula for M and N is C4H4O4. So based on that, we can find HDI. So for 4 carbon atoms, maximum number of hydrogens we can have is 4 multiplied by 2 plus 2, which is 10, but we only have 4. So difference divided by 2, it gives us 3. So it has HDI of 3, which could be many things like 1 ring, 2 pi bonds, or 3 pi bonds. We don't know. It could happen. There are a lot of possibilities. So let's just put everything together. What we know about M and N. They are geometric isomers. They both have the molecular formula like this. They have 4 oxygens, 3 HDI, and they should have alkene functional group for Diels-Alder reaction. Because it's going to be really easy to construct the structure for this molecule because we only have 4 carbon atoms. If you have more carbon atoms, it's going to be really difficult, right? But we only have 4, and we already know that 2 of them should be like this because we need to have alkene functional group, right? In order to react with this diene according to Diels-Alder reaction. So we have our 2 carbon atoms and we also have 4 oxygens. So I am actually assuming that this compound is symmetric for now. So I can put 1 carbon here. It's just an assumption, right? I'm not 100% sure. I'm just saying because that makes things easier. Now I have to think about C2H2O2 and I have to double it, right? That makes things easier. Probably the person who made or people who made this question they also are aware of the fact that among all possibilities, you cannot just randomly construct a structure for any molecular formula with 4 carbon, 4 oxygen, 4 hydrogen. It's impossible. So it's better be symmetric. Let's put it this way. That should be your first assumption, because otherwise it's going to be a really time-consuming task just to construct the structure from a molecular formula. So I have to assume basically that this is symmetric. And I also have 3 HDI. I also used one of them here. So I am left with 2 HDI. So since I am using it symmetrical, so I should have 1 HDI in each side. 1 HDI here. When I say 1 HDI, I mean a moiety that contributes to HDI, which could be a ring or a pi bond. Because I already have double bond in between, so this is already 1 HDI. So I need 1 HDI in each side. So by having these, everything together, and I also have 4 oxygens, so 2 oxygens should be here. And can I have a ring here? Because I also have just 2 carbons here, so 2 carbons here. I'm just putting it here and 2 hydrogens here. So I hope it makes sense, right? So I have to use C2H2O2 on this side and 2 carbons here. I have to connect them this somehow. I hope it makes perfect sense. We are getting there. And then this should be connected in 1 HDI fashion, right? They cannot make any cycle. If that is the cycle, then you have to make oxygen bond, which is really unstable in 4-membered ring. And in general, 4-membered ring is really unstable. So I don't think we can have any ring with this small number of atoms. So it's highly probable that we have a double bond. Oh, we have only 1 carbon atom. Sorry. So these carbon atoms are actually within this. So within this double bond. So I only need actually 1 carbon atom in each side. Sorry about that. And so 1 carbon, 2 oxygen, and 2 hydrogen. So what I can do here is I can have COOH, which is carboxylic acid group. And actually it makes perfect sense. If I have carboxylic acid group here and carboxylic acid group here, and one of the hydrogen will be here and another hydrogen obviously will be in the double bond. So that actually satisfies our requirement. And I can also have geometric isomers in this case. So this structure for M and N makes perfect sense. Now that we have found the structure of M and N and it makes perfect sense, it fits all pieces of information that are given. They are geometric isomers. These are cis, COOH and COOH are on the same side. So these are cis and this is trans. Now that we have 2 geometric isomers for M and N respectively, we can find out the structure of other compounds. And I see respectively, actually it's wrong because I don't know which one is which. I don't know if, or this is M. This we will be able to find out if we consider the structure of O, P, and Q, or the information that one of them yields 2, for example, M gives 2 of them, but N only gives 1. So actually this is enough for us to find out which is which. So let's go back. So we have this scheme, hydrocarbon 1 reacting with M and N, M gives O plus P, N gives Q, and I'm putting everything together. This is my hydrocarbon 1. With M, which is cis isomer, I get 2 products. With N, which is trans isomer, I only get 1 product. So why this is the case? Because as you can see with cis isomer, I have this COOH group. They are both endo. So what does endo mean? It means if you consider this similar to cyclohexane conformation, every time it has axial and equatorial, you can think of it like this, or maybe just up and down, or you can just think of it as this bridge. You have this bridge here, we call it as a smaller bridge, and you have another bridge like larger bridge. So you can also think of it as a position that is opposite to small bridge. You can think of it like this. So endo conformation is where your substituents, your groups are on the same side, are cis to a large bridge. And exo is when you have those groups trans to each other. So go this, if you can think of it like this, if you want to see this bond, you see like this. So this goes up, these groups goes up, but this goes down. So your bridge, your larger bridge, and your compounds are trans to each other. But in this case, they are on the same side. So this bridge and these compounds are on the same side. They are cis to each other. So we call this as endo. So when you use cis isomer, there is a chance that both of them are endo or both of them are exo. So that's why one of them is going to be O and one of them is going to P. And that makes M as cis isomer. So if you remember, we had cis and we have trans, but we didn't know which one is N and which one is M. So, but now we know that cis isomer should be M because cis isomer is the one that gives 2 products. With trans isomer, you get just one of them exo and one of them endo. it doesn't matter. You don't have another case, because if you just put here endo and here exo, like the opposite, it's still the same. So you don't have two different compounds. So when you use trans isomer, you only get one. So I see here, I take a look at here, I get one compound here, Q, so that makes N as a trans isomer, but I get O and P here, which means two compounds here, that makes M as cis isomer. So I was able to differentiate between cis and trans, and I was able to label them as M and N respectively. So now Q is easy as well, because which is same as here, 1 react with N to give you Q. So this part is easy. And in here, they actually gave us information about relative distribution of the products. It says O is 85% and P is 15%. So here, endo transition state is more stable than exo transition state. So when we make this compound, when they react, we have a transition state, and we are conducting this reaction in kinetic condition. If you remember, it was 20 degrees. We don't use any high temperatures or something like that. So since we are using low temperature, we favor the formation of kinetic product. I will come back to this again, kinetic product, thermodynamic product. So the one that forms faster is going to be major product here. So here, endo transition state is more stable than exo transition state. So that means O is going to form much faster, and that's going to be major product. So I will come back to this again. And also I want you to take a note that I didn't say endo product is more stable than exo product. I am just saying endo transition state is more stable than that. So I will come back to this again, because question number 4 is directly related to this. But here O is going to be both endo, because O is the major product, 85%, and P is the one that's going to have both groups in exo position, because it's minor product, just 15%. And we are done with question number 3, and lastly, they ask us to draw a qualitative energy diagram for the reaction of hydrocarbon 1 with M, given the fact that it is thermodynamically less stable than P. So we already know this, right? So we have hydrocarbon 1 reacting with M, which is cis isomer, and there's are two possibilities, compound O and compound P. In O we have both in endo, and in P we have both exo. And they told us that O is thermodynamically less stable. This is given fact, but O is 85%. How is this possible? If O is less stable than product P from thermodynamics perspective, then why we are not getting P as our major product, right? Why O is predominating in the reaction product mixture? The reason is because it's a kinetic product, and we are conducting reaction under kinetic conditions, low temperature for 20 degrees, right? So yes, it is thermodynamically less stable, but it forms faster. So that's why it's kinetic product. And then we are going to have an energy diagram like this. This is our starting materials, I plus M. And if you see here, for O, which is a blue line, it has lower activation energy because it has lower transition state, even though P is more stable at the end. P has a lower energy. But it depends on how we are carrying out the reaction. Are we carrying out it in kinetic conditions, or are we conducting it under thermodynamic conditions, for example, high temperatures? So this directly affects the product distribution. So in this case, why compound O is a kinetic product, let's explain that one. So when we form Diels-Halder reaction, when we are writing mechanism, so what happens here is that we have our diene and we have our alkene, right? It has COOH and COOH. So when we try to form cyclohexene ring, we are going through this transition state that looks like this, but here, instead of full bonds, we are having partial bonds, right? We are forming this bond. Okay, I will just show it like that here. And we are forming our pi bond here as well. So this is the transition state that leads to O. And as you can see, I am having this in endo position, so I'm going to write it in an open form. So this is electron withdrawing group, and I am forming a pi bond here. So there's a favorable interaction between developing pi bond and electron withdrawing group. There's a favorable interaction here, and that stabilizes transition energy. So when you stabilize transition state, energy of transition state is going to go down, which is going to make activation energy lower, and that directly increases the reaction rate. So that's why it's called kinetics, because kinetics is the study of reaction rates. Anything that forms faster in certain conditions, we call it kinetic product. So this is the reason why endo transition state is more stable than exotransition state. So when you see this graph, this O is both endo, right? Endo, endo. And the transition state here is obviously gonna be lower energy transition state because of favorable interaction. So we will have this gap here between exo transition state and endo-endo transition state, and that will make product O faster. Because we are only carrying out reaction under 20 degrees, we are not supplying a lot of heat or something like this. So obviously the product that forms faster is going to be major product. That explains full thermodynamic profile of the reaction. And if you wonder why, even though transition state for endo product is lower in energy, why at the end of the day we have O product? The reason is, if you see the structure for O, you will see that the COOH groups are cis to this large breach. So there's a steric interaction here. So just this is a similar reasoning to why cis alkenes and trans alkenes, if you compare them, trans alkenes are always stable. Why is that? Because in cis alkene, your groups are on the same side, so there is some steric interaction. So you prefer them to be located from each other as far as possible. So that's a similar reason here, right? So even though they're electron withdrawing, they're stabilizing transition state energy, but at the end of the day, they are cis to large breach, so that destabilize this overall structure at the end. So that's why P as a product is more stable from thermodynamics perspective. But since we are not employing thermodynamic conditions like elevated temperatures, we have O as our major product. Now all parts are complete. We are done with our first problem. If you want the original problem and the full step-by-step solution, just check the forum in the description below and I will email them to you. Thanks for watching.